Recall that Stembridge proved that irreducible character immanents of totally non-negative matrices are non-negative, and he conjectured the same thing for monomial trace immanents. Haiman proved that irreducible characters evaluated on Kaj-Johnlistic basis elements are polynomials in Q with non-negative integer coefficients, and he conjectured that the same thing holds for the evaluation of monomial traces. So we have similar theorems and similar conjectures, and that's not a coincidence. Let's look at what the connection is between these. Let's let D be a planar network with path matrix A. So every path family in D has a weight which is the product of its edge weights including multiplicities if two paths take the same edge. In that case, we'd have to take the weight of the edge twice. So think about which path families have the same weight. Well, that's easy. It's the path families that use exactly the same multiplicity of edges. We should say the path families would share the same multiset of edges. And this weight really depends only on that multiset. So let's call it the weight of K. So it's a product of edge weights in K with multiplicities if several paths use the same edge. Now let's define capital Pi of K to be the set of path families covering K. And let's let capital Pi W of K be the subset of those that have type W. Then let's associate a group algebra element to Pi of K. Actually, a group algebra element just to K. So this is going to be an integer linear combination of permutations. And let's let this be the sum over all path families that cover K, the type of that path family. Now Stembridge proved that if theta is any trace, or really any linear function, then the theta imminent of A is equal to the sum over all bijective skeletons the weight of that bijective skeleton times this function theta applied to z of k. So to see this, for each permutation W and Sn, let's look at the product A1 W1 through AN WN that comes up in the imminent. So this is the sum of weights of path families of type W. Now we could separate out the path families that share a bijective skeleton. So let's sum over first over K, a bijective skeleton. Then we can sum over pi covering K and having type W. Weight of that path family. But the weight of all path families covering a fixed bijective skeleton is just the weight of that skeleton. And then if we're pulling that weight out, I guess we're just summing over summing one here. So if we sum 1 over all the path families of type W covering K, that's just the number of path families of type W covering K. So now let's take this first expression and the last expression and multiply them by theta of W and sum over all W. So that's how we get the imminent. So multiplying by theta of W and summing over W and Sn. We have the theta imminent equal to the sum over W and Sn, theta of W, then sum over bijective skeletons K, weight of K, number of path families of type W covering K. Let's sum over K first. And then sum over W and Sn, theta of W, number of path families of type W covering K. Now theta is a linear function. This is just a number. So we could pull theta outside of the sum and look at the linear combinations of W defined by these numbers. So this is the sum over K, weight of K, theta of sum over all W and Sn, W, number of path families of type W covering K. Now every path family here is counted next to W, which is the type of that path family. So we can rewrite this as a sum over K, weight of K, oops, I forgot the theta, sum over all path families type of the path family, because W is being counted as many times as there are path families of type W covering K. So if we sum over the path families themselves, for every path family we're counting type W. That'll give us the right coefficient here. And this is the sum over all bijective skeletons K, weight of K, times theta of, now this is precisely the definition of Z of K. The sum over all paths and the sum of overall path families covering K, the type of that path family. Alright, now let's take a look at what Z of K looks like. So Z of K is some rational number times a product of Cauchy-analytic basis elements indexed by reversals. So for some rational number p in some intervals I1, J1 through IR, JR. To see this, observe that K is a union of n paths. And if no two paths share an edge, it ends up being a star network. In that case, Z of K has the desired form. With this number P just equal to 1. Now if K paths share some edge, or some sequence of edges, let's say there's K paths all running together on certain edges here. Then Z of capital K is 1 over little k factorial, what it would have been if the K paths were separated into K different roots here. So that's where we get this rational number from. Because if we expand each of these edges, we can get a product like this, but then we're lying by a factor of K factorial. So we keep having to divide by integers there, and so we end up with some rational number. All right, now let's look at what this product of Cauchy-Johnlistic basis elements looks like. So if we have a product of two Cauchy-Johnlistic basis elements, that belongs to the span with coefficients that are polynomials in Q with non-negative integer coefficients of Cauchy-Johnlistic basis elements. So the proof involves intersection cohomology and is in a paper by Springer. All right, and now I can state the connection precisely. So we have the following implications. Concerning the Hecke algebra trace, I should say a Hecke algebra trace theta q and the ZSN trace theta that we get by specializing at q equals 1. So first of all, theta of q evaluated at a Cauchy-Listowel basis element is a polynomial in Q with non-negative integer coefficients. So it sort of obviously implies that theta of the Q equals 1 specialization is a non-negative integer. And then that implies that if we apply theta q to a product of Cauchy-Listowel basis elements indexed by reversals, that gives us a polynomial in Q with non-negative integer coefficients, which also implies, let me back this up a little bit, that if we specialize at Q equals 1, we've got theta being evaluated at a product of Cauchy-Listowel basis elements of the symmetric group algebra being a non-negative integer. So we get that from here by specializing at Q equals 1, we get it there by Springer's result. So this is, let's say, IV. And that implies statement 5 that the theta imminent of A is greater than or equal to 0 for all A totally non-negative. So the proof part of which I said as I was writing it, so 1 implies 2 and 3 implies 4, just when we specialize at Q equals 1. So substituting Q equals 1, we go from 1 to 2 or 3 to 4. Then 1 implies 3 comes from Springer's result. In particular, so if this product of Cauchy-Listowel basis elements equals, let's say, a sum of FW C prime W actually it should be Q's then theta Q of it meaning this here, is the sum over permutations in the symmetric group FW of Q theta Q of C tilde W. So if we know that this is a polynomial in Q with non-negative integer coefficients, we're multiplying by more, then we're going to get a polynomial in Q with non-negative integer coefficients. And this is really the same for 2 implies 4 also. Then finally, 4 implies 5 is Stembridge's result. That the theta imminent of A is a sum over all bijective skeletons in a certain planar network. A non-negative weight associated to that times theta of essentially a product of Cauchy-Lustig basis elements like that evaluated at 1. So then we have the following corollary, that Haiman's conjecture that monomial traces of Cauchy-Lustig basis elements are polynomials in Q with non-negative integer coefficients for all lambda a partition of n and W and Sn implies Stembridge's conjecture, which was earlier, that monomial trace imminence of totally non-negative matrices are greater than or equal to 0 for all totally non-negative matrices A and for all lambda a partition of n. The end.